covering the non-functional property of performance, security, and resilience of network system, and their underlying protocol. Marinho Barcellos has regularly contributed to the network research community also by serving on multiple committees. In addition, he currently chairs the advisory board of the ACM PACM Net Journal. Today, his talk will focus on a close look at remote peering. Please join me to welcome Dr. Marinho Barcellos on the stage.
Thank you for the kind words. Good morning, ladies and gentlemen. So let's have a look on remote peering. So, but I would like to begin thanking the organizers of this event. So for bringing me here. New Zealand is far, far away, tucked in a corner of the world. So it's a long journey. It's a major effort. So thank you for allowing me to be here in Thailand, in Bangkok, and attending this wonderful event. I shouldn't be impressed, but I am. It's really amazing. I'm going to present joint work with a few students, Fabrício Mazzola, Pedro Marcos, and Augusto Setti. These were my students. Fabrício, in particular, is defending his PhD on remote peering in a couple of weeks. This is also joint work with Leonardo Almeida, who is a reseller engineer, and also Professors Matthew Luque and Inácio Castro, earlier one in this work. So the path for this keynote, the plan for the presentation is to begin with an overview of remote peering. Then I'll proceed to the inference of remote peering because there's some opaqueness and it's not trivial to infer remote peering. Then we'll discuss how prevalent or how important is remote peering on the wild, on the internet. Then routing issues that may arise because of the use of route peering and remote peering, and then we need to be aware of these potential problems. Then I will compare remote peering with local peering, especially in terms of latency, but not only. And I will suggest, I will report the use of BGP communities for the sake of traffic engineering of remote peering in IXPs, and I will wrap up with my final remarks. So let's begin with an overview of remote peering. And even before that, the reason we are here is internet exchanges. They are awesome. So there are over 850 IXPs spread in over 200 cities worldwide, and they interconnect over 50,000 networks. Okay, it's a small fraction of the internet, but it's really, really, really important. So IXPs vary a lot in terms of size, well, what is size, but number of members or exchange capacity, traffic rates, age, how long they are on the road, if they are single or federated, their business model, if they're NGO or what, or the business. So, but anyway, peering infrastructures are super relevant, and they are leading forces in some regions of the globe, probably here too, but also in Africa and South America. So for example, in South America, we have Brazil, which has a very strong IXP ecosystem. It's a federation, it has over 25 IXPs, and it has the largest IXP in the world with over 2,500 members and lots of traffic. So if you show here, for example, the aggregate of traffic through a decade, you see that now that large, huge IXP, it has over 10 terabits per second of traffic, and it's been growing and growing. This is just one IX. But actually, it's not one IX, is a federation of IXPs spread over a large mass land, which is Brazil in this case. And we have several of these IXPs which are large and relate even with the BKNICs. And we'll be reporting measurements that we've done and some insights that we obtained based on these IXPs. So the peak rate has exceeded 14 terabits per second in this largest in the world. And the overall IXBR ecosystem has peaked, I think, 21 or 22 terabits per second. So it's quite a lot. So IXP and remote peerings. So in this maybe academic view, very simplified view of an IX, we see there that there are two colocation facilities, number 1 and 2, with the switches there. And so these facilities are interconnected. We have the ASs A, B, C, which are local peers. And we also have, potentially we have like ASH, which is connected to one of the facilities via IP layer 2 transport. And we have a reseller. So a remote peering reseller is an entity that allows some networks to connect to the IX, not being physically present at the IXP, at the colocation. So the remote peering resellers represent a key factor in remote peering. So they provide access to the IXP, usually connecting routers of the remote ASs to the IXP layer 2 fabric, and using L2 transport, and along with contractual IXP membership issues, like typically with a VLAN. So these examples of these remote peering resellers are abundant. This is one, it's called GlobeNet. It's one of the largest ASs according to AS rank. Here we have another one, a local example, like that's being considered or works here, Console Connect. Well, this remote peering resellers, they have two roles. One of them is to bridge large geographical distances by connecting ASs from far away from the IXP, or also to facilitate or reduce the costs, like peering equipment and its installation, allowing ASs to easily connect to the IXPs. So these two, like they're not mutually exclusive. But kind of the two main things with the remote peering resellers. So I'm an academic, I'm faculty, I do research, but we sure need to consider the remote peering benefits or use cases. So I see at least three. One of them is to fetch the content from content providers that are far away. They are available directly into a remote IXP, but they are not available nearby. Secondly, in an attempt to improve the quality or the latency of when you have clients that use latency sensitive applications such as cloud gaming, video streaming. There's several applications nowadays on the internet, and we do a lot of traffic engineering to try to get the good performance, and remote peering can help in that respect, certainly. And finally, market share. So it is possible that remote peering is useful or is used to try to avoid a network, an ISP, a regional ISP, for example, being bypassed by a larger upstream provider. And we will illustrate an example of this, and this works by making the regional ISP more attractive in terms of BGP. So let's suppose we had the ocean, and the ocean was calm, life was easy, and we see there, like at the bottom, we have kind of a client, a local ISP, and And that local ISP is served by a regional ISP and then connects to a major operator, and that major operator connects to the, or reaches to the international content. So life was fine for the regional ISP until one day, yeah, the big fish cuts the small fish. In this situation, what happens is that the major operator realizes that, yeah, it could reach to the local ISPs itself and bypasses the regional ISP. So, well, the regional ISP could fight back and use remote peering to reduce the path length and become more attractive in terms of BGP. And in that case, you see with the blue connection between the regional ISP and the content provider. So in that way, the content might go through the regional ISP instead of the major provider. Of course, I mean, there's no right or wrong here. There's no wrongdoing or anything with the major provider, with major upstream. It's just kind of like they're fighting for a market. So there are many claimed benefits of using remote peering or a reseller, such as lowering the cost of peering, for example, by sharing a port. So in that case, there's a minimum capacity that IXP will allow networks to connect. And if you're using a reseller, then the reseller might buy the port and then share through several smaller clients. So that's one advantage, because then the cost is lower. Also reduce the cost in installation. So by eliminating the need for additional hardware. Also to simplify or make the setup easier by automating or outsourcing the process. So now you have a reseller to do this for you. And mainly, for example, in the case of an international connection, so you have content, for example, you have content in Europe that you wanna fetch. You want to have a presence in far away internationally, in US or in Europe, and then you could use a remote peering or reseller to avoid bureaucracy of establishing a business overseas, because there's law stuff that you need to be present there, contracts and stuff, purchasing network hardware to deploy there at the coloc, renting rack space in a colocation facility, and finally paying for a maintenance team. So all these are costs and things, or hurdles that would disincentive someone to be present at an IXP far away, and a reseller can help a lot. What we see, and we'll back this up with some data, some results I'll tell you later, is that remote peering sometimes is used as an initial step, as an initial approach to get to a remote place and evaluate if it makes sense or not. So there's good things. I mean, many people praising the use of remote peering, but on the other hand, there is some mixed feelings, or people that are not happy about the use of remote peering. So this is a controversy. So, and one reason is that because it breaks the premise of keeping the traffic local. So the core, the essential reason why XPs exist is to keep local traffic local, like a bypass, avoid transit. So by using remote peering, this premise is broken. Also, the opaqueness of remote peering, because all connections, in theory, they look the same, but they are not the same. Performance will be quite different, and so, but you as a network engineering, you should know, well, you would like to know, especially if a cloud provider, for example, you want to know which connections are remote and which are not. Remote peering adds a third party, which adds complexity, and it is harder to monitor and debug. So for example, some of the problems that have been reported are regarding Anycast, which is fundamental to a lot of things like such as cloud networks. So if you use Anycast, the problem is that with remote peering is not visible to at layer 3 at BGP level. So so if you are using Anycast, perhaps it looks like the content is nearby, but is not, it's far away. So there has been a paper that found exactly this. And there are also issues like outages and things like that. So these are some of the posts that have appeared against the use of remote peering, saying like we shouldn't throw around remote peering links everywhere, like this is kind of the wrong way of going. And so people are unhappy about the use of remote peering. Things like, oh, it's like transit, but even worse, things like this. So we have done a measurement study on remote peering. We've been doing this for some time now, for a few years. And because it's a relatively understudied topic. And so we started measuring and connecting or like collaborating with several IXPs to get their data and do measurements. So in this keynote, I'm reviewing key points and providing data and insights about remote peering to inform the discussion without trying to reach a conclusion, actually. So our measurements were based on a set of vantage points and data sets. So we have a set of IXPs that we have tapped into, that we have considered. And in some cases, depending on the measurement that we were doing, we had to limit the set of IXPs because what they offered and kind of a ground truth they could provide and so on. We also have like BGP data from Packet Clearing House, archive, Alicia Looking Glass when the IXP had a Looking Glass available, and Ralph Views, the Ralph Views project to provide us BGP information. So the period was between May 21 and August and October 2022. So I would like to first distinguish between two types of remote peering. They are not actually two types because these are they are not mutually exclusive, but there are different ways of considering or approaching remote peering. So one of them is geographic remote peering, and the other one is reseller remote peering. So again, as I said, they can be together, but there are different approaches to remote peering. So in case of the reseller information, we had the ground truth from some IXPs. So they told us, oh, these are remote members and you can measure and be sure that your measurements are right. And we love that. This is very important for any empirical research. And also we on orange there, we have 3 ASs that are also remote peers, and they are inferred as remote peers as of the geographic type, because we'll see later the latency, the round trip time is at least 10 milliseconds or larger. So the first thing is how to identify the use of remote peering. So imagine a discussion like this. I was wondering which interfaces were remote in that IXP. Why do you want to know? Because I want to apply special BGP policies to them. I, want to treat them differently. Well, identification may be tricky, So how to identify remote peering connections? So remote peering is opaque, as I mentioned before. So inferring remote connections has been a problem long known in the academic world. And the first attempt to identify the use of remote peering actually was a paper that coined the term remote peering was in Connects 2014, a collaborator of mine, Inácio Castro. And that was the first attempt. It was based essentially on latency and some additional information. And that was used to identify instances of remote peering, and basically using that threshold of 10 milliseconds. A second attempt was made later on in 2018, IMC, the Internet Measurement Conference from IMC. And in that paper, they showed that the previous approach was flawed in many ways, like it was identifying remote peering when it was not, and vice versa, with some margin of error. And so they developed further. They even use machine learning, but and they got much better results, like 90% identification of remote peering connections. But however, they found that the most important, the most relevant feature was still the latency and collocation information. And then we did a study that we showed that their approach was limited in many ways. For example, it was based on PDB information, and oftentimes PDB entries are not there, like in some regions, like in Latin America. Unfortunately, many networks do not update PDB information. So it was inaccurate for several reasons like this, and then we come up with a different strategy. So how to identify remote peering connections? So we take advantage of route views, the project route views collectors, and we run a tool called Scamper to do trace routes and pings. And we ping the interfaces inside the LAN of the IXP, and so like there can be no change of a TTL. And so we measure the latency in that case. And we use as the source IP address for the green measurements. You see the green arrow there from Scamper route views to ASA. And in that case, it's like a simple ping, and then we get the latency. Of course, we do this over time to be sure that we are getting the values right. We also do some kind of spoofing. We change the source address of our pings and trace routes from sent by the Scamper. They are sent through the IXP LAN, but they have the source address T1, which is the source address of a transit provider. In that case, what is happening is that the packet is going to the remote peer or not, and going back through transit. So in that way, we can discover many things. So how prevalent is remote peering? I mean, in the wild, on the internet, is it popular or not? So do you know how relevant is remote peering to the internet? What do you mean relevant? Relevance can be understood in many different ways. Well, like prevalent, like widely used. Tell me more. So one of the reasons for looking at different aspects of remote peering is that prefixes and routes cannot exactly match the level of members of interfaces. So it's possible that they are not directly proportional, like more members, more remote members, more remote routes. So the question is what to count and what are the trends? Is it increasing? Is it decreasing? So we had a lot of questions as scientists who wanted to answer. So number of members, number of interfaces, like saying number of remote prefixes, address space size, actual traffic volume, which would be great, market size, revenue. These are all relevant questions to understand how remote peering is important, how much remote peering is important. And what we can do is that we look at members, interfaces, prefixes, and routes. So broadly, in terms of members, we found that in terms of reseller remote peering, so like how many networks use rich IXPs through resellers, is, well, the number varies among IXPs depending on their size and so on. And we found that around 1/3 of the members in this huge IXP, the largest in the world, reached to the ISP São Paulo remotely, like via reseller. and 1/4 in links. Again, I mean, take this with a grain of salt. It's like a doctor telling, yeah, I examined you, and last week your temperature was, I know, 39 degrees. And that's the information. Like these things are changing all the time, as we will show. We also found that remote members connect to IXP to reach large content cloud providers, okay, discussing with the networks involved. And specifically in this Brazilian ecosystem, they are scattered in this huge land mass. So in terms of geo remote peering, so when they are really like at least 10 milliseconds apart, and we suppose, you know, like 1,000 kilometers, a large distance. So over 1/4 of the ASs in the three largest IXPs were a geo-RP. So like the IX of Amsterdam or like the KICS, this kind of thing, they have a large number of networks that are remote, that are distant. And the IXPs with fewer incidents of geo remote peering, they had a lot less, and then it was like a 10%, more or less. Well, before discussing the prevalence of remote remote prefixes, because kind of one thing is the number of interfaces or number of remote peers, another is the number of prefixes. So we need to distinguish between three kinds of prefixes: the local ones, the remote ones, and the hybrid ones. So hybrid is not a great word in this case, but like local prefixes are the ones that are only announced by local members. The remote ones are the ones that are only announced by remote members, remote peers. And the hybrid is a case where we have a prefix that has different routes, via local members and routes via remote members. So it's like there's a choice. Where should I send my traffic to? So in terms of prevalence of remote peers announce proportionally fewer routes than local peers, both for reseller RP and geo RP. So kind of you may have a large number of remote members, but actually that doesn't translate into a number of remote prefixes. So remote peers use remote peering selectively, which is the right way, by the way. And use local XPs for the rest. We observe a sizable number of hybrid prefixes. These are, as I said, the prefixes that have routes that are local and remote, and in that case, there's a choice. So in particular, links and Amsterdam, and also in US, you know, Equinix Ashburn, Equinix Chicago, over 70% of remotely announced prefixes also had a local one. So, you know, it's often the case that you have a remote route and you have also a local route. Do you know if the number of remote interfaces and prefixes is growing? So longitudinally, like I want to know, is this a trend or what? Yes and no. Well, tell me more about it. So we compare the values for the number of remote interfaces and remote prefixes in these IXPs, like the largest one in the world, which is São Paulo, then Links in London, Napa, Africa, Rio de Janeiro in Brazil. The next one is also in Brazil, and then the two Equinix ones in US, Ashburn and Chicago. So in terms of remote interfaces, what we see is that well, we had like a 31% and then 13%, 7%, 13%, 35%. So it varies between the among the IXPs, the level of interfaces that are remote. This is actually an underestimation because of the latency of 10 milliseconds, the threshold. But anyway, it's at least as high as that. And we see that from May 21 to October 22, what happened is that the number of remote interfaces only grew. So we have more and more and more use of remote peering if the metric is the number of remote members. So yeah, remote peering is growing. I mean, you could say like if you want to convince someone, yeah, remote peering is the way. Like there's more and more and more. However, for remote prefixes, we see that in May 2021 and comparing to October 2022, the percentages that are in red mean a reduction. The ones in blue are like more or less the same. And the red and the blue ones means it's increased. So we see that overall, what happened is that there was a reduction in the number of remote prefixes. So even though there was an increase in terms of remote members, there was a decrease in terms of remote prefixes. So more members, but announcing less, which is okay. So this is exactly the same conclusion turned into words. A number of remote interfaces has increased, but the amount of aggregated growth varied according to the characteristics of the IXP. So in that case, for example, if you have well-established IXPs that have been there for a long time, they have a consolidated member base, and so like there is less space to grow, which is not the case in, for example, Napa Africa and some other IXPs that are smaller. Okay, and as I said, decreasing number of remote prefixes. So amazingly or surprisingly, I mean, you would expect for one single IXP, okay, there was an increase in the number of members. Certainly there was an increase also in the number of prefixes. And no, it was not the case, even for like a single IXP, because you see, if you are counting the number of members over a set of IXPs and number of prefixes, it might be that like overall something grew and the other one decreased. But actually in every single IXP, it was like this. So it is kind of staggering. So for most IXPs, on 5 out of 7, the number of remote prefixes decreased from 21 to 22. So by using remote peering, are there any routing issues that may come up, like with remote peering, you know, like any problems? So let's suppose we have 2 IXPs, one local and one remote, and 2 networks, A and C. And in this case, I mean, what the network operator intended was that scenario where like ASC or ASA is getting content from ASC. And that was because the announcement that was done by ASA was a /24, and /23 of the same prefix was announced to the remote IXP. And that is fine, it's absolutely what should be done. But instead, because of a mess up, it was configured differently for some reason, probably mistake. And the more specific prefix was announced to the remote IXP, and the less specific prefix was announced to the local IXP. So what happens is this, what we see in the picture, the red dashed arrow represents the traffic going from ASC to ASA via the remote IXP. So this was happening a lot in some places with international connections. So kind of, let's say Brazil, to provide a concrete case. So we have 2 networks that are in the same city and traffic was going to Europe and back. So a terrible situation cost-wise and latency-wise. So how much this is a problem? So we wanted to measure this, and we picked BGP data in 22 along with the ping measurements from vantage points in IXPs to corresponding IXP member interfaces. And we identified the ASs that were present in multiple IXPs with the like potential for this what we call trombone paths. And so with 1 connection and 2 or more remote connections. For these ASs, we check the set of prefixes as they announce in more than 1 IXP. So we identify the potential cases. And in the set, we see the size of the prefix announcement. We compare and see if there's a potential for a trombone path. Just recalling that because of BGP, that there's a choice. The preference is for the more specific prefix. So this indeed is a problem. We quantify the daily number of trombone prefixes and identify the ASs that were announcing them. And we did this over 2 months, and we observed almost 500 trombone paths, trombone prefixes per day. Well, this, of course, I mean, we expect this to be a transient problem, not like, it shouldn't be something that stays for months, right? So that's why quarantines and things like that exist. But anyway, it was a lot. Thank you. So to demonstrate the what the problem was, or like to identify what the problem was, or who were the culprits is a strong word, but that kind of thing. So we checked the pairs of IXPs that could have these trombone paths, and we see a lot of, unfortunately, a lot of Brazil and a lot of in links also. And we display just the larger ones, the 93%, the ones that have more than 1,000 occurrences. So let's compare remote peering with local. So in the case of prefixes, both local and remote routes, is local or remote peering better? Well, define what you mean better. Well, the shortest path, the shortest AS path, I expect remote to be shorter, right? It's indeed the case. So we compared the path length in hybrid prefixes and AS path lengths of hybrid prefixes show in the graphs. The majority of hybrid prefixes had remote routes with an AS path length shorter or the same length as the local route. So again, the remote routes were shorter in terms of AS path. So they tend to be preferred, and that was the case. So, and indeed they are preferred. So we used the route view BGP collectors to analyze what routes were being chosen by the members of the present at the route view collectors. And unfortunately, the remote routes were being picked because they were shorter. So it was not just like a theory, it was, yeah, there's a problem here. But wait, if remote routes tend to be preferred, can this be bad? Well, it could if the remote latency, if the latency via remote peering is larger. So let's compare. So we pick these 4 XPs in which we have Scamper running on the route views nodes. We see the total number of prefixes that are hybrid. That means that have local and remote routes. And this first case is remote peering has lower latency, but longer AS path length. So remote peering would be better, but will not be chosen because the AS path is longer. The second case is remote peering has lower latency and equal AS path. Then that we don't know what the tie break will be. The third case is local lower latency. So remote local peering is better, but it has a longer AS path length. So it tends not to be preferred, even though it is the best one. And you see large numbers there. And finally, local peering has lower latency and equal AS path length. So if you focus on these 2 cases in the rightmost, these are troublesome because they show that like local connections, local peering is more efficient, has lower latency, but is not being picked, is not likely to be selected. Ouch. If left alone, there could be a latency penalty. Yes, indeed. How about variability in latency? Because could remote routes be more stable? So this is something that remote peering resellers sometimes claim that like, my connection, my direct connection will provide more stable latency, less jitter. And we measured that, we couldn't see any difference actually. We hoped to see, but there wasn't. So we say in New Zealand, Kiwis say, yeah, nah. They couldn't find any relevant difference. Oh, maybe the robustness of remote interfaces will be superior. I would not expect that. You know, like having a local connection is likely to be more robust than a long one. And yeah, not really, lower availability and stability of remote peering connections. So we measure this in terms of BGP sessions with the route server at IXPs, at in the Brazilian ecosystem and in London. And every 15 minutes, we took a snapshot. It's not perfect, but it's all right. So we looked at the uptime between failures and number of state changes over time. So these are simple measures just to see if the connection was stable for a long time or was disconnecting or what. And not surprisingly, we find that the local connections are more stable. They have a larger uptime between failures. That means the purple ones compared to the green ones. And comparing also in terms of number of state changes, BGP state changes with the route server, not surprisingly, the local ones have fewer changes than the remote ones. Maybe not a big issue, but not large margin, but yeah, it could be another factor to consider. Finally, we also compare the latency between with remote ASs. So this is like initial steps. We investigated how remote peering compares to transit providers latency-wise when used by ASs to reach prefixes announced in international IXPs. So we compared 4 transit providers and 2 large IXPs, and then in this scenario, we have like this really long distance connections. So we also used the BGP data for the control plane and did active measurements using a VM infrastructure inside the remote peering reseller. We looked at the maximum round trip time and round trip time variability. And I'm highlighting there that the best latency for around 20% of the prefixes was with remote peering, and it was second best in another around 20% of prefixes. So the takeaway lesson is that like remote peering can be great, but it has to be used with care. Right? So this, by the way, these results applied for both links and AMS6. And when comparing prefixes that are both on Amsterdam and London, they were the same. Like there was no distinguishable difference in performance between these 2 IXPs. And these are preliminary results, as I mentioned there. So with the difference in performance between local and remote peering connections, could the IXP help us guide our decisions? Yes, it could. So in March last year, the Brazilian ecosystem started offering traffic engineering BGP communities to control route propagation based on latency. So there are 2 BGP communities, like actually more than 2, but 2 kinds. One is no export if latency is over a given threshold, and the other one is prepend X times if latency is over that threshold. And the IXP itself starts measuring latency to members. And I'll show the results for the IXP BR São Paulo, January this year. And we see that the most common one is the prepend one. Like prepend ones if RTT is larger than 10 or larger than 50 milliseconds, and that was quite common instead of no export. But still, just to highlight that the use of BGP communities related to remote peering for traffic engineering is really at its infancy. So like it's a very powerful tool that I would recommend. I think every IXP should implement that because it gives more information to all the network members, about like more control, and this is good. Okay, final remarks, some takeaways. So increasing number of remote interfaces. I mean, we see an increasing number of remote interfaces, but with fewer remote routes overall. So on one hand, there's more remote peering over there, over and over. It's growing, but not necessarily in terms of remote routes or remote prefixes. Despite having higher latencies, remote routes tend to be preferred, unfortunately. Remote, and this is down to configuration. Remote interfaces are less stable and less available than local ones, no surprise. Possible routing issues with more than, we found possible trombone paths with more than 37,000 prefixes on the IXPs that we analyzed. And finally, few ASs tagging small number of routes with remote peering, traffic engineering, BGP communities. So like again, you know, until this information percolates in the community, it takes some time, but eventually this will become popular, and a suggestion for BKNIX to implement this. Okay, we would like to peer, to collaborate, so increasing the set of IXPs we consider data from, partnership with IXPs in APNIC, partnership with ASs using remote peering, and this is to understand better the use of remote peering in their networks and provide better performance and resilience. So you cannot solve a problem until you understand it. You cannot understand the problem if you don't measure. So you need to measure the use of remote peering. And so we'd like to extend the analysis for IPv6 because it was limited to IPv4. And also we'd like to consider security implications about remote peering, which was not done so far by anyone. Okay, so I appreciate your attention, your time. And thanks again for the organization for inviting me to be here. I'll be around answering questions, and I hope there's some time to questions now, but otherwise I'll be like in the coffee available to answer any questions you have. Thank you very much.
Thank you very much, Dr. Marinho Barcellos, for a great talk. So next is the connectivity session. We have two fascinating presentations